Hello, this is Craig. Welcome back to the Valve Studio. We're going to do a little housekeeping before I get started. I got an email from YouTube last week saying I'm now eligible to monetize my channel. You need more than 1,000 subscribers and more than 4,000 view hours in 12 months, and you can monetize your channel. I didn't even have to think about it. I just said I'm not doing that. I'm not going to make you sit through a Rogaine commercial just so you can watch my video on how to do tube amplifiers. It's ridiculous. I didn't do this for the money. I did it because I'm figuring out things along the way, and I figured that you as a watcher or subscriber to this channel are interested in the same type of topics. So we're not doing that. All right, let's move on. The last time we were together, I was talking about with this amplifier, I had screwed up some measurements because of the input impedance of my digital multimeter. And then I have a subsequent video on why this is important. And on this amplifier particularly, there's several high impedance nodes, and by putting your voltmeter in there, you affect the voltage level at that node. I took a lot of care in this video to actually measure what those voltages were, and I confirmed that this particular design has a low screen voltage. It turns out it's about 16 volts, which is really low, and I couldn't quite understand. Well, I never really knew what the impact of the screen voltage is on using a pentode for a preamp stage in a guitar amplifier. I have a good idea what it does in the power stage, but not using it for a preamp. So it's been a stumbling block ever since I got started with doing looking into tube amplifier design. What is the impact on a pentode of the screen voltage? Why is it 150 in some designs and it's 30 in others? I didn't quite get it, but now I do. Now I have it. I spent an enormous amount of time in the evenings trying to figure out what the deal is with the screen voltage. And there's some significant advantages of using a pentode for preamp circuits, because you can tailor the characteristic performance of your amplifier in ways that you just simply cannot do with a triode. Now, a lot of you are saying, well, you know, the Vox, the early Voxes used a pentode in their preamp and they were microphonic. So pentodes got a bad rap at that point, and hardly anyone uses them. But I have hundreds of pentodes back here. I might as well use them. There's a lot of advantages to using them, and I talk a little bit more about that. And in this video, I really address the performance of the Kamico amplifier, and I actually measure some performance and look at some theoretical values and some data sheets. In the next video, a future video, I'm going to talk a lot more about the impact of the pentode screen voltage. All right, so where are we at? Let's get started. So this video is really long. I apologize for that. I start out by looking at the circuit itself, and then I look at some data sheets. Then I measure the performance of the amplifier on my bench using test equipment, and then I measure the output from my Gibson with humbuckers in it and a tele clone that's got single coils. And then we conclude up, we'll have the conclusion. And if you want to skip around, I will have some time points in the description so you can move to different points in the circuit. In the video. So let's get started. All right, just a quick review of what we covered previously. This is the entire amplifier, and it has a power supply over here with an 80 rectifier tube, field coil speaker, and we're using a 6F6 output power pentode and a 6SJ7 as the preamp tube here. So I'm going to go over what I have today in the lab. Is I've taken all this section out, and I'm driving this circuit with a high voltage power supply right here, and I'm using a filament transformer on in the power transformer. I'm using the filament voltage to power this voltage here. So let's zoom in on the preamp circuit. So this is it here. The bolded numbers here are what I actually measured, And the things I did do with this was this resistor is A20K on the grid down to ground, control grid, and this actually doesn't exist in the amplifier at all. This cathode bypass capacitor was bad, so I replaced it with another one. And the last time we were measuring things is when I made some mistakes because of the input impedance of my meter. Went through carefully and measured all this again. I also removed this screen bypass capacitor, which is a 0.1, and I checked it, and it is good. And also this 0.1 coupling capacitor over to the volume potentiometer, it is also good. So I put these back in, and what I found over here was we put in 315 volts on the power supply, and this is supposed to be 390K, but it really measured out to 418, 2.4 mega ohms, measured out 245, and this one down here was supposed to be an 820, but turned out to be 840. So we're going to live with what we got in there now. And what the like I mentioned earlier, the stumbling block was this 16.1. I'm going to go over a little bit about this today, but not very much. I'm going to save that, like I said, for later. So measuring this voltage here is actually pretty interesting because if you think about it, if you put your meter in right here, there's a 10 mega ohm resistor right here, and there's effectively a resistance from the screen down to the cathode. And so you have a voltage, and then there's a current that runs through here. So this is effectively a resistance for DC bias perspective. So it really kind of looks like this here, where you have the power supply up here. Here is your meter input impedance, and this is the reading on the meter. And then you have this unknown resistor here. And you can, if you know this voltage and you measure this one, you know what this is, and you also know what this is, you can determine what R2 is. And then if you take that and you take a reading, if you take a reading on the real circuit with your meter, and then you use all those four numbers, this one, this one, this one, and this one, you can calculate what R2 is. All right. Then from there, what you can do is effectively take this out of the circuit theoretically, and now you're left with the screen resistor and the screen impedance, and you can determine this reading a little bit more accurately. So what I measured, I didn't actually measure 16.1. I measured something a little bit smaller, but I did go through and run some calculations on this particular circuit here, and I derived 16.1 based on, I determined the screen resistance over here. I determined that, and then from there I calculated out what that is. And I did the same thing up here on the plate voltage of 91 volts. Okay, so this, like I said, this has always kind of thrown me, this low voltage here. So let's go ahead and show you that it's not a fluke. It's actually part of the design, I believe. Here is a schematic for a friend of mine. In town, he is on Craigslist a Bogan HE10, which is a PA tube amplifier. And I got the schematic for it, and wouldn't you know it, it has a 6SJ7 as a preamp, and you probably can't see this, but the plate voltage they're running at over here, the bias voltage is at 37, and their screen voltage is 20 as well. So I kept looking. This is an iCore PA. This is actually a amplifier out of a tape recorder for an iCore Model 400. And it uses an SJ7 for the preamp tube as well. This plate voltage here, the bias voltage, is at 120 volts, and the screen again is a really low voltage at 16. So I'm going to, like I said, I'm going to talk a little bit more about why this is so low in the next video. But today we're going to go through and talk a little bit about some sheets that there are some graphs that show up in these data sheets. I have I went over to Frank's and got these data sheets out. This is for the SJ7 from General Electric, and this one over here is the RCA SJ7, and they actually have different information in them. I found in my studies here that GE data sheets are a little bit cleaner because they're a little bit newer, and there's just a lot more information in a GE data sheet. So we'll just go through here. We're not going to look at any of this stuff because typically, these characteristics here are written by the General Electric or the RCA engineers, and they're giving you the values here that'll give you the optimal performance in terms of distortion. But you can see from here, if we're running the plate voltage at 250 volts, they suggest you run the screen voltage at 100, but we're running actually at 16, so none of this actually applies. Okay, these graphs here are pretty common. This one up here shows you if you were to ground the control grid and the screen grid. This is basically the characteristic curve if you're changing the plate voltage. If you're changing the screen voltage and you vary the plate voltage, you get this type of curve here. So this is one type of data sheet that you get. Now down here, this one here is changing the, it's holding the screen voltage constant while it changes the grid voltage. So this is typically the graph used for biasing. You know your load, you plot your load on here and you figure out where you want your bias point and all that. Okay, where it gets a little bit tricky is you can't use this graph because this is at a plate voltage of 100 volts. And what you use these two graphs together, and what it basically lets you do is this entire graph is done at a screen voltage of 100, and this one, this graph up here, so basically all these curves will fit in this area down here because this line right here, the 100 volt line, is the same as this line right here. So all these fit in here. If you were to lower it down to 75, all these lines would smash into this area. And if you lowered the screen even more down to 50 volts, all these lines would fit into here. So we're at 16 volts, so our line is basically down, like way down here. So all these lines are going to fit in this little area down here, which makes it, pretty difficult to do anything. So with low screen voltages, these curves don't really show you what you want to know. However, if we keep going, this is a tryout operation. Here's the transconductance. We'll come back to this in a minute. These graphs here, these are actually the transfer characteristics. These show you with different screen voltages, if you vary the plate voltage, if you vary the grid voltage, you get out a certain amount of current. So this graph right here is really redrawing these two together and putting it on this graph. So this is the graph you need to kind of find when you're doing Pentode design, because this enables you, if you were to pick 150 volts and you put minus 4 volts in there, you would get out about 7 milliamps. Okay, so here's 150, 125, 100, 75, and 50. Now we're at 16. So let me get my pen here, and we'll just etch in where 16 would be. Now, where did I put that thing? Here it is. All right, so 25 is going to be kind of in between this line and the origin. So I would kind of estimate the 25 is going to be, I don't know, maybe about here, like this maybe. And 16 is even farther down. So 16 is going to be, I would say, a little bit more than half. So I would say 16 is about like this. Now this is a small signal pentode, So they don't they don't recommend you do positive grid biasing where you'll have grid current. But if you were to look at tubes that are pentodes that are designed to handle grid current, these curves actually continue over on this side of the y-axis, and they all shaped pretty much the same shape when they get over here like this. But like I said, this is a small signal, so we're not going to use this portion of the graph. But my point is that all these curves basically look the same, and the lower you go in the screen voltage, the shift of this kind of profile moves this way. All right, so this is 16 right here. This is my estimate. Now our bias point that I measured was 0.6 right here across. So this is basically minus 0.6 on the grid. All right, let's so minus 0.6 is about here. This value is 1. This is 1 milliamp here. So right here we are probably about 0.4 milliamps. All right, now I'm a little bit higher than that. On my measurements, I measured the plate current at 0.54, which is, so I'm close. It is down in here somewhere, way down in here. I'll give you a spoiler for the next video. If I have a 500 millivolt signal coming out of the guitar, and say I pick a value over here somewhere, let's say I pick right here, and I have let's say we get on the right at 2 volts, 500 millivolts will swing to here, down to, well, this is 3, yeah, so 500 will be 250. So we'll be swinging about here, which is a pretty straight line. If we take that same 500 millivolts and we run it across this one, this line is really curvy right here, and this is going to lead to distortion, which is kind of what you want, but we'll talk about that next time. All right, this graph down here is a screen current in terms of milliamps. This one is the plate current. So this will tell you down here, if we do that same thing again, here is, I would say, 25, and 16 is about here. 0.6 will be over here, so this is going to be, this is 0.25, and the screen current is probably going to be half of that, so 1.25 milliamps. All right, so I measured 0.125. This measurement, or this estimate, is 0.125 milliamps, 125 microamps, and I measured 121 microamps. Okay, so we're pretty close to the design portion, and what that means is that I haven't messed up the measurement portion of this significantly, because my measurements are actually getting near where the designer actually decided to put the bias point. All right, let's look at something else here. The previous graph over here is the transconductance in micromhos. The transconductance, G sub m, is equal to the change in, it's the change in plate current. So we got I plate over the grid voltage, VG. So that's what G sub m is. Now, what you're going to see here is, let's say we do the same thing again. We'll draw in a 25 graph, 25 voltage graph on the screen, and we come in, so I'd say maybe about here. This is pretty horrible estimate. And then the 16 is going to be down in here. Okay, now our bias point is going to be 0.6 minus 0.6, which is about here. And this value over here is about 500 500 micromhos, which is amps per volt. All right, so that's 500. We're going to go through and take some real measurements with the circuit, and we're going to try to determine if we're anywhere near that number as well. Okay, now here's the part about, this is the part about doing design with pentodes. It's all about this graph right here. You probably haven't really looked at this graph and really understood it, but this is the reason why I had to take a break and really understand all this. By changing the screen voltage, I can modify the G sub M value for my tube. If I choose a higher screen voltage, I can make my G sub N go from now 500 all the way up to, say, 3500. Because of that, I can definitely control the output swing on my resistor loaded pentode, and I can change the impedance level at the plate. Because if I say I wanted a 5 volt swing on the plate, down here this is such a low voltage, I could use a very low resistance. If I use it up here, I need a larger resistance. Is that right? Yeah, I think that's right. Anyway, so because of the screen voltage, it lets me have a lot of flexibility in all these different parameters in terms of G sub M, the plate current, the grid current, the screen current. All this stuff is pretty much variable. That's the key to the whole thing. Now this RCA has one additional graph that you don't have over in the General Electric one. So we have the plate characteristic. Now this one here is the same graph as the previous one. This is the plate current in milliamps based on the screen voltage. But this one goes down to the bottom graph is at 25 volts. So there's one additional line on this graph than there is on the GE. I'm going to keep going here. So this is the last graph that's part of the RCA Pentode data sheet that's not in the General Electric. And so this shows you what G sub M looks like if you vary the grid voltage with a specific screen voltage and a specific plate voltage. So if you were to pick a small bias point for your control grid, you would get a large G sub M. If you pick a larger voltage coming in, a larger bias voltage, you're going to get a lower G sub M. Now, you can see this if you think about what this is actually showing you. You can see this in the graph that you normally look at. All right, if we look at this graph here, well, let's look at the RCA one because it shows it even more prevalently. All right, so here's the plate characteristics for the same tube, and we're at 100 volts on the screen. And what you're looking at with that G sub M graph is you're basically looking at the space between the two lines. So these voltages are -5, -4, 3, 2, 1, and 0. So if you're down here between 4 and 5, you're getting this much swing on the current. All right, if you come up here, you're going to get that much more swing on the current. So when these are not spaced equally, you have control over G sub M by picking your bias point on the grid. And you can choose that, and this last graph in the data sheet on the RCA shows you that. So this graph over here actually shows you that G sub M gets large as you go down in the bias point selection. All right, I hope that makes sense. I don't, if it doesn't, that's fine. You just it took me quite some time. I'm talking about months, probably / years, to come down to get into the point where I kind of understood the selection of the screen voltage. All right, let's get on to measuring the performance of this Kamico amplifier. All right, here's our test setup. We have the amplifier here. I don't have a rectifier tube in it. I don't have the Pentode power tube in here either, but I am using the power transformer for the filament voltage for my 6SJ7, which is over here. And in order to get the filament voltage to be right, we're using the variac here, and I dialed in my filament voltage to be 6.3 volts. What else do I have here? So that's on the running the heater in my 6SJ7. Right here I have a ammeter that's connected to my high voltage power supply in series with my power supply, which is up here. This is a ISCO model 490. It's an electrophoresis power supply, and I found this over at the Habitat Restore, and I bought this for like 15 bucks, and it's a great power supply. It's super clean. It goes up to 1,000 volts at 150 milliamps. So keep an eye out for these power supplies around for your tube amp work, because they're definitely less expensive than an HP or a Kamico high voltage power supply. These work fine for what I need to do. So I have that voltage dialed up to about 315 volts, and the current reading on the front of the power supply kind of matches up with this current down here. This current on this meter down here says this is a 1 milliamp full scale, so I would say it's about 7.2. All right, now if we add up our currents, we got a 534 microamps and 121 microamps, which works out to be 650 or so. So we're a little bit off, and which is fine. I have no idea about the calibration on this. This Weston meter here is probably older than I am, and I don't know anything about its accuracy, but it's close enough. It's showing me both the screen and the plate current. Up here, I'm driving it from an AC perspective. I have a function generator, and I have it properly terminated. So I'm coming out on a coax here, and I have a 50 ohm termination resistor down next to it's right down here on the guitar amplifier's input jack. And then over here I have an HP spectrum analyzer. We'll go ahead and show you some spectrum of the waveform once we run it up and show you distortion characteristics. And then down here I'm just showing you this is a scope connected up to the input to the grid on the control grid on the SJ7, and then the output is right across the 500K potentiometer. All right, that's all said there. Okay, so let's first measure the gain. So what I'm going to show you is I have the frequency at 1 kilohertz, and the amplitude is 100 millivolts peak to peak. And this scope has a couple of nice features where it does some measurements for me. So the peak to peak voltage here is 20.2, and that's on the output. The input is 114 millivolts. So if we kind of get an estimate of what that gain is, Alexa, what's 20.2 divided by 0.114?
28.2 divided by 0.114 is 247.3684.
Alexa, what's 20.2 divided by 0.114?
20.2 divided by 0.114 is 177.193.
Okay, so that's showing us the gain of the amplifier at 1,000 hertz at 100 millivolt drive signal. Our gain is 177, which is fairly high. Let's look at this voltage level. Let's look at the microphonics. So what I'm going to do is I'm going to tap the tube with my fingernail. Okay, oops, we got to get this back over here while it's running. Okay, you're seeing a little bit of a variance in the signal there on the output signal, but it's not much at all, and I'm really thumping it. Okay, so we may not have any microphonics issues. We might be able to run this Pentode at that high gain level. Now, if you go over to the Valve Wizard website, there's a whole section about using Pentode Preamp tubes, and the Valve Wizard advocates that you can get a lot more. There's a lot more flexibility and tonal characteristics of Pentodes because you do get to control the screen voltage. But he does say that Pentode tubes become more microphonic the higher the gain they are, which makes sense. And he advocates for doing the Pentode design less than a gain of 100. We're at 177 right here, and we're not really seeing any. So we might be good. The vibration that is reflected into the amplifier from an 8-ohm speaker is unknown at this point. We're only going to have to figure out, if it's good enough. But the point of this thing right here at 1K, we're putting in 100 millivolts of signal, and we're getting out 20 volts of output voltage, which is good because we need to drive the output tube, which is a 6F6. We need some high voltage swings to actually drive that up into getting its output power. Let's first move up to, let's measure the frequency response. So 20.2, the 3 dB point for 20.2 volts is right around 14 volts. So what we're going to do is ramp up the frequency generator first on the high end, and we'll show you that. So I'm going to go to 20K first on the frequency. And then we'll show you this over here. And right now we're at 15 volt output swing. Our input voltage is still about 100 millivolts, and our phase is 100. Went down from 180 down to 139, which is we're close. So this amplifier runs all the way out to 20 kilohertz very easily. Let's go back down on the low side. What I do want to show you is it does have significant frequency response because, the input voltage has a little bit of noise on it right here. You can kind of see that it's a little bit fuzzy on our input voltage. Let's go down and measure the low side. So the low side, let's first go to 50 hertz. 50 hertz is where? Nope. 50 hertz is that one. 50 hertz is back down at 14. Okay, so which is great. So the amplifier, this thing's kind of squirrely on me. It doesn't want to trigger right. There we go. Okay, so this is kind of the low end of the frequency response, which is 50 hertz, which is pretty good. It's fine for this amplifier because we're driving an 8-inch woofer, and we probably don't even want it to go that low. So we may end up modifying the cathode capacitor value to move that 3 dB pole up a little bit, so it's more like, this 3 dB frequency is at 100 hertz or so. All right, let's keep going. So that's good. Let's go over and look at the spectrum at this point. First of all, I want to show you what the spectrum of the let's go back to 1K first. At 1K, and we're at an amplitude of 100 millivolts. So I'm going to first show you the amplitude output from my frequency generator and show you the distortion characteristics of only the frequency generator. So we're going to go back over here. And for those of you who are old like me, you know what this is. This is a spectrum analyzer, and it basically does a sweep of a narrowband filter across the band that you have set up, and this will go up to 50 kilohertz. And if you really are familiar with this thing, I have these knobs kind of not set very well, but for today's purposes, we're not measuring real performance. We're just looking for the spectral content. So what I'm going to do is we're going to dial this up, and I'll show you that this frequency generator I'm using is very clean. So this is the fundamental, and it is at 1 kilohertz, and you can kind of see, right, let me get my pointer up here. This is a 1 kilohertz peak, and then the second peak is going to be right here, and you could kind of see it. No, you can't see it really, but this is 10 dB per division, so we're 10, 20, 30, 40, 50, 60, 70, 80, about 85 dB down. So spectrally wise, this frequency generator is actually working really well in terms of its putting out only the fundamental. And it is a synthesized frequency generator, so you expect that kind of performance from this. Okay, let's go back to our amplifier here. So I'm going to plug this back in to the amplifier, and we'll click that back down, and then we will click this back up here. All right, so now we're back to that. Now, there's a little nuance again with the impedances. This is a 10 meg ohm input impedance on a scope because I have a 10x probe, and I have that across the next stage gain, the volume pot actually. All right, so those two in parallel are the change of 500K is not very much. All right, but this unfortunately has a 1 meg ohm input impedance. So when I connect up my probe voltages here, what you're going to see is the blue wave here, the output waveform is going to go down a little bit because we're loading down the circuit more. We've put an extra 100K or 1 meg ohm resistor across that 500K pot, which drops it down. So we're going to get a little bit of reduction in the voltage, but spectrally wise, we're going to get to see what the spectral content of the output voltage is for this preamp stage. All right, so what you're seeing up here is here's our fundamental, and about 10, 20, 30, about 35 dB down is a second harmonic. So that's desirable for this particular kind of amplifier, is to be primarily even order harmonics. And we're at 100 millivolts over here. So if you look at books that talk about the output from a humbucker coil versus a single coil, like in a Tele or a Stratocaster, you get strong signals more from the humbucker because there's more coil wraps around the magnet. On a humbucker, it's about twice as much as a single coil. And you could expect to get, from what I read, which we'll look at here in just a minute, 100 millivolts is pretty common for a humbucker. 50 millivolts. This is as the signal decays because the string stops vibrating. You should expect maybe 50 millivolts over average. Well, we can go look at that, but first we'll look at that in just a minute. For various types of pickups, but this is at 100, 1 kilohertz at 100 millivolts. So let's go up to 200. millivolts. All right, now you're seeing a little bit more down here. You're seeing the second, and the second is now down 30 dB. Here's the third. The third is down about 85 dB, and the fourth is down at about 80. No, this is about 75 dB, and this one's about 80. All right, now we're going to run off the screen up here, so I need to change this setting here. Okay, so you can see that this is the second, and this is a little bit of the third, and a little bit of the fourth. That's at 200 millivolts peak to peak. Let's go up to 400 millivolts peak to peak. We'll see what that is. All right, now we're seeing more harmonic distortion. Let's turn this down over here so you can see the time waveform. On your scope, it looks pretty good, okay? But the spectrum analyzer tells all. So we have, here's the second. It's down about 25 dB now. The third is down 1, 2, 3, 4, 5, about 60 dB down. And the fourth is down about 80, 70. It's about 7, yeah, about 70. All right, so let's keep going. Now, remember, the bias point on this Pentode was 0.6 volts. So we should be able to, really put in like almost a volt into this amplifier, which will be, that's a volt peak to peak, which will be half a volt positive. So we'll go up to about 0.1 volts on the grid. And when you get close to zero on a grid, for the control grid, you're going to start seeing grid conduction. And on a small signal Pentode like this, you don't want to really drive the grid very positive, because the current flow out of the grid will actually cause it to heat up, and there'll be a little bit of a power dissipation there. So we're going to stick to voltages less than 1.2. All right, that's 400. Let's go up to, let's go to 750. See what that is. All right, now we're getting even more harmonics. Our second is down 20 dB. The third is down 40. What is this? This is the fourth, the fifth, the sixth. So now we're really getting some kind of distortion. And your waveform here is now kind of looking a little bit distorted, because this peak is kind of rounded off. Okay, and this one's getting a little bit narrow. All right, that's expected. All right, let's go up to 1 volt and see what we get out. 1 volt. And we'll dial this back a little bit. And get over here, raise that up a little bit. Okay, now we're at 1 volt. So we're almost off. We're exceeding the capability of this thing the way it's set up right now. And we may be actually distorting the input stage on this, so we got to turn that down. We can't drive it so hard. I would like to bring up a point here by putting in 1 volt. Down here, we're putting in 1 volt. And we're getting out 144. So this voltage swing here is really there's a large voltage swing. You would never get to this high, but I'm just making a point here. So now we have a measurement issue. We need to turn that down a little bit. So let's go back down to 950 millivolts. No, come on. 950 millivolts. That's still on. So let's go down to 900 millivolts. And it's still on over here. All right. Yeah, I don't think we can change that one. Yeah, it moves it up. Okay, we got to go to 850. 800. Wow. Can't go much higher than 750. Can't even do that. All right, so let's keep going down, because I think the measurement we took at 750 was wrong, because we are overdriving the input stage of this, and the spectrum analyzer is going to actually show you the distortion from the input stage here. I think all we're going to be able to put in here is 600 millivolts. Okay, this spectrum analyzer won't take more than 100 volt input. All right, but even at 600 millivolts, you can kind of see that we got our fundamental, second, third, fourth, fifth, and sixth, and it's fairly distorted, even though the waveform on the scope looks okay. All right, so we have enough numbers now to actually look at G sub M. I'll come back to that in a minute, but let's go look at some guitar signals. I'll get out two guitars. I have a Gibson with humbuckers, and then I'll go get out a Tele clone. It's got single coil on it, and we'll see what kind of voltages we get out, and look at the time domain of the voltage coming out of both guitars for the different pickup arrangements. All right, so the first off, we're going to use the Paul model. I bought this in a pawn shop in 1981 in Santa Barbara. And what I've got going on the scope over here is we'll single trigger it, and we got the level set kind of high, so we only get the first one. So I'm going to be in the middle position with both volume knobs up and all the way to 10, and my tone knobs are all the way to 10 as well. So I'm going to play an E chord, and we're going to capture the E chord on the scope, and we're going to be able to look at the peak-to-peak amplitude of the output from the guitar signal, as well as the output from this Pentode preamp. Okay, so we got 900 millivolts on 900 millivolts peak to peak here, and we got 152 152 volts out. All right, let's do that again. This time I'm going to be on the bridge pickup. This time we got about a volt out and 150 volts in. That's pretty high. I hit this pretty hard here. All right, this one I got at 1.3 volts peak to peak and 176 volts out. So this is quite a bit higher. Let's play some single notes. First, we may have to change our triggering a little bit. We will play, what are we going to play here? I guess we'll play E. We'll play E on the fifth string. Okay, we're not. We got to lower our triggering level. Got to get it down here. Let's do a little test here. All right, good. Okay, so I'm going to just pick a string, E, the E note on the sixth string. All right, this is not hit very hard, and it is 330 millivolts peak to peak, which is still kind of hot. Let's flip the pickup over, see what the other pickup does. And I think I can turn this down a little bit. Yeah, let's turn it down to 100 millivolts. So we'll do the same string. Oh, we're not triggered. All right, this is 250 millivolts. And we're getting 48 volts out. All right, let's do a little high string here to see what we got on the E at the 12th octave on the first string. All right, this is get 200 millivolts here, and you can see from the waveform it's fairly constant. I get 36 volts out. So this guitar here, when its volume knobs are all the way up, we get a fairly substantial signal out of these humbuckers on this this old Gibson guitar here. So let's switch over to the I have a Tele clone back here. Well, I'll go get that. I'll be right back.
Okay, we're going to move over to my tele clone. This is one of those Indio clones that I got from Monoprice for, I don't know, $97 or something. And it needed a little work, so I took it over to my friend Jerry, who's my guitar and amp tech here in town. And I said, Jerry, fix this bad boy up. The fretwork was really bad. Well, whatever. I don't want to talk about that. But it is a nice guitar. I mean, if you started out playing guitar and you got one of these first, you would it'd definitely be a step up. So, all right, I got the volume knob all the way up. Get my scope triggered. And these are single coils now. These are single coils, so we'll see what kind of amplitude we get out of this guy. So I think I need to, let's just hit it and see what we got. All right, that's a hard chord, and this one puts out 500 millivolts peak to peak for an E chord in the front position. Let's see what the back position is. I guess it's the bridge pickup. You gotta be careful not to touch the guitar. Here we go. Nope, we triggered again. Damn it. So sensitive. No. It's tricky. All right, we're still good. Be very quiet. Oh, man, we clipped. Okay. All right, we've got to turn down the signal amplitude here. This is, again, the E chord. All right. Peak to peak on this guy is 944 millivolts. So we're getting 152 volts out. All right, so how about some single notes? Because the documentation, I mean, if you read books, they say, Telly's put out 50 millivolts. Well, I think that or single coils, I think this guy is going to do a lot more than that. So we'll just pick an E string here. There we go. That guy was 150 millivolts peak to peak there. So this is still pretty hot. We were to, let me see here, I'm on 50 now. All right, let's try this again. Let's not pick it so hard. That's a light touch, and that is 200 millivolts. So this guy puts out between, 100 and almost a volt. 100 millivolts, almost up to a volt. So either guitar could clearly drive this Pentode up into the hundreds of volts, which is what's going to get fed into the potentiometer, so we can change the voltage level going into the output tube, which is a 6F6. But we have plenty of drive signal, and this has plenty of gain. So, all right, one last thing to look at is the G sub M, our calculated value, or our estimated value for G sub M. We got that off of this one graph out of the data sheet by extrapolating. This is for the transconductance in micromhos. We kind of drew in a 25 volt line for the screen voltage, and then I kind of estimated where the 16 volt was, and I came up with 500 microamps. 500 microamps per volt, or the micromhos. All right, so let's go see if we get this number. All right, so the gain of this circuit, because this the output impedance at the plate is really high, we kind of neglect that. But if you want to look at this from a circuit perspective, we have a current source that is G sub M times VG, well, cathode. It's this voltage here. We'll call this VG. And then that goes into this resistor, but remember now this is on the AC side, so this is effectively, ground, this power supply up here. So we have 418 ohms here, 418K, and our 500K pot here. So this is our equation, or this is our circuit, the equivalent circuit to the output of this from an AC perspective. So 418 and 500, 418K and 500K. This is equivalent to 228K resistor. All right, so this is little r sub p, which is the AC equivalent for the plate, the impedance that the plate sees. So in a pentode, the voltage gain is equal to G sub m times little r sub p, and our voltage gain at the midpoint, which was 1K, we had about 200 volts over. No, we had, what do we have? We had 20.2 over about 0.1 volts. All right. So 20.2 over 0.1 is 202. So that's our voltage gain. So if we plug everything in here, we get 202 equals G sub m times 228K. So G sub m is equal to 887 micromhos. All right, our data sheet said we should get about 500, but we actually measured 887. All right, so the reason why this might be off a little bit is my estimation of where these curves actually lie, but there's something else on the RCA data sheet. This one's the GE, remember. All right, so this same graph on the RCA actually has a 25 volt line on the graph. So that's this line right here. So this is 50, this is 25. So 16 is going to be, I would say, I don't know, maybe here, like this. Something like that. And our bias voltage is 0.6 volts. So here's 1, here's -1, and this is minus 0.6 is going to be this line right here. So we're a little bit closer up. This is probably 600 or so. Micromhos. So we're close. We're close on the estimation of G sub m. Okay, let's just hop back to my desk and let's wrap this up. Okay, if you made it this far, I hope you learned a little bit about the flexibility of using pentodes for preamps and the selection of the screen voltage and how it impacts G sub m. And that enables you to control the impedance of the output, the plate impedance of that particular preamp. And from that, you can tailor the sound in different kind of ways. We didn't really address non-linearities at this point. We kind of looked at it a little bit, but there is some additional flexibility in using pentodes to introduce non-linearities, which makes it really attractive in the preamp stage. We'll talk a little bit more about that in future videos. So we actually looked at this. The performance of this amplifier has got a gain of nearly 200. From the bandwidth is 50 hertz up to almost 20 kilohertz, which is really high. We may end up having to put a little bit of low pass filter in the amplifier to kind of knock down the high frequency response. But we won't know that until we actually plug this in and couple this SJ7 to the 6F6, the output tube, and actually put the amplifier together. We'll do that in future videos as well. So again, if you made it this far, thanks for watching, and this is the Valve Studio.